Okay, today's video, we're looking at Unit 4 Study Guide. I have a collection of about 20 or so different questions that we're going to work on. Feel free, as you need, to skip around and kind of just look at the questions that you need help with. No need to waste your time doing ones you already know how to do. Keep in mind, any of these questions that you kind of work out and give to me on the date of your test, I'll give you some extra points on your test for that. It's broken down into three main subtopics. Chapter 12 for us is all about kinetics. That'll be the first thing we talk about. And then I'll go over the topics for that in just a minute. And then we're going to talk about chapter 13, equilibrium, and then chapter 13 is thermodynamics, chapter 14, equilibrium. And those three topics together make up your test. So feel free to use this video as a way to kind of check your work or help you if you're stuck on any of these problems that you can access the whole PowerPoint to on Schoology if you'd like. Okay? So either work along with me or use this to check your work as we go. All right? So our kinetics topics that we're going to be looking at today, kind of what I have listed here are 8 of like the skills you kind of need to answer questions that will be found on your test and on the AP exam. And each one of these has a practice problem that goes with it to kind of show you, because some of these words might not mean a lot to you. So we have average rate from a data table, rate of appearance or disappearance using a chemical reaction, rate law from a data table, order of a reaction from a rate law, order of a reaction from graphs, looking at variables that affect the rate of reaction, and then some keywords, intermediates, catalyst, overall reaction, rate law, reaction coordinate graphs of a reaction mechanism, and then some first and second order half-life problems. Okay, we're going to go into each one. I'm mainly just going to be working on my document camera, so I'm going to go ahead, switch over to that, and we're just going to go through each of these questions in order. So we have question 1 here. It says, the following table represents the concentrations over time during some random reaction A turning into B. So we have the time passing. So at time equals 0, my initial concentrations. I have some of A, I have some of B. And it looks like over time, A is going down, which makes sense because it's a reactant, and the arrow shows it proceeding to the right, and B is going up. My question here is, what is the average rate of A, so I'm looking at A specifically, over the interval between 10 and 20 seconds. So I want to find what is the average rate of change of A over this time interval. All right, so when I get to a problem like this, I don't have a real formula I'm going to give you for this, but we're basically just using the slope formula. So rates, or average rate, you just treat it like y2 minus y1, so y, over x2 minus x1. That makes it easier for you to kind of think about. Y being your concentration, X being your time. Okay? Or the way you might see this written more would be like rate is molarity 2 minus molarity 1 over time 2 minus time 1. And writing it out this way is probably more accurate. It gives us the actual units of rate, which is good. So either way you write it, but you're writing the same thing, especially if you write it correctly and write a 1 there. Okay, you're going to your second time. So I'll just use this bottom formula because it's the same. My second molarity would be my second one, 0.024, minus molarity number 1, my starting molarity, 0.03. My times, okay, time 2 is 20 seconds, time 1 is 10 seconds. So I get this expression, 0.024 minus 0.03, divide by 20 minus 10 is 10. So I'm going to plug that into my calculator. All right, so 0.024 minus 0.03, negative 0.06. I'll just divide that by 10. And I'm going to choose to write this in scientific notation. But if you don't, that's okay. Negative 6 times 10 to the minus 4th. That is my average rate that I'm looking for. And since it is a multiple choice question, it doesn't really matter how you write it. Okay. A is my right answer, so we can kind of check our work there. Oops. So negative means it's going down, which adds up if I look at that. And then some of these other multiple choice must have been if you did your math a little bit wrong. All right. Next question. Getting the rate law from a data table. Let me try to focus on this a little bit better. This is the most common sort of question you're going to get. Definitely want you to know how to do this. Definitely going to ask you all about this on your test. I have multiple trials where I've varied the amount of A and B in my reaction. And I've recorded the rate of the reaction as a result of varying the amount of A and B. What this allows me to do is if I want to learn about A, how changing A affects the rate of the reaction, I can just look for 2 trials where A changes, but everything else is held constant. And for example, for A, it gets cut in half. So times 1/2 as you go between 1 and 2. But B stays the same. So this is a good opportunity to learn about what changing A does. Cutting A in half, how does that affect the rate? Well, 4.2 times 10 to the minus third, going to 2.1 times 10 to the minus third, you're cutting that in half. Right? My exponent's staying the same, but 4.2 is getting cut in half to 2.1. So that one's also being cut in half. What that means is a change made to A, you see an equal change to the rate, meaning with respect to A, we are first order. All right, B, we'll look for 2 trials where B is the only thing changing. A is held constant in 2 and 3, but B doubles. Over here, if I look at my rate goes from 2.1 up to 8.4. The only thing I've changed is now I doubled my amount of B, but my rate has increased by magnitude of 4. Okay, that means doubling my amount of B has had a squared effect on the rate of the reaction. So this reaction, if I'm thinking about just B, is second order. The third option that you'd really see is if there's no change. Say I doubled the amount of B and my rate stayed exactly the same, we would know that's 0th order. When I go to write my rate law, I always start with this first part's always the same, rate equals lowercase k, and then just put in brackets each of the things that affect the rate. A affects it to the first power, so I'll put A and just leave it so it's to the first power, and B affects it squared. And that expression is your rate law. That's what you're looking for. Okay. A very common question to follow that up would be to solve for the rate constant little k. And all you need to do is plug in, you can pick any of the trials, you get the same answer. The rate, so maybe like that rate you'd plug in there. The concentration of A, be like the concentration of A, concentration of B, concentration of B. And then you could use that to solve algebraically for k. Here we have a follow-up to the last question. We want to know the order of a reaction from the rate law. Okay. All right. We already wrote the rate law. Not sure why I made this a separate question, but it'll give you an easy point on your test. So make sure you do this one. All right, the order of the reaction with respect to A. I guess mainly just to focus on this language, the respect to A is talking about just A's exponent, which would be first order. What I think I meant to ask you here instead, and I'll kind of just add that to the bottom, is what is the overall order? That's not even close to how you spell order. Overall order of the reaction. And to get that, you just add the exponents together. So because you have 1 and 2, add that together. This would be a third order overall. And that's, I guess, probably what I meant to ask you here, but that'll work as well. All right, for the next one, this is a little hard to see. I'm going to go back to the PowerPoint for this one. If my head's not too bad in the way, let's move it down there. Okay. So 3 graphs were made to represent an experimental reaction. What is the most likely order of the reaction? So I've this is some real data sets that I made on Excel, and I've graphed 3 different quantities. So over here on the left, this first one, I have the concentration, how much you have, its molarity, versus time. Okay, I can kind of look at this reaction, and I don't have a normal data table, I just have the graph. And you could see that this isn't a completely straight line, it kind of has this little curve in it. Okay. And what that tells you, because there's a curve in this line, is that this is not a 0th order reaction. 0th order reactions are completely linear if you look at their concentration versus time. That means it goes down at a completely flat level. The amount you have doesn't affect how much you lose. The second way you can check a graph to figure out the order of a reaction is if you take the natural log of the concentration. So over here, I took the same data set, and now instead of just writing the normal concentration, I took the natural log of it first, and then made this other graph. And you'll see this one's way straighter. To check how straight a line is, you can use this value called an R-squared value. And the closer it is to 1, the straighter the line is, right? And you can see this line is very close to 1, 0.99 basically. So it's a very straight line. If the natural log of the concentration versus time is straight, it's a first order reaction. And that's probably what this one is. And just to check, I graphed the 1 over the concentration versus time. And you can see this is the worst graph so far. This isn't even close to being linear. The R-squared is 0.75. So because of that, if this line was straight, it would be a second order reaction. So all you need to put for this one is the answer is this one is the straightest line. Therefore, this is a first order reaction. You'll never really be responsible for making these graphs yourself. But if I give you these 3 graphs, the key is that you're looking for which unit is on my x-axis. If it's regular concentration, that corresponds to a 0th order reaction. The natural log corresponds to a first order, and 1 over the concentration corresponds to a second order. Remember, knowing why takes a little bit of calculus knowledge. Maybe you can understand this relationship if you've taken calculus. How is the natural log of x related to 1 over x? That might be kind of familiar. You can think about some derivatives or some integrals, depending on which way you go, right? And concentration's kind of related in a similar way. You don't need to know that, though, if you can remember which one corresponds to which. Okay. All right, another one that I don't really need to work out, because this is kind of just a conceptual one, is which of the following factors should increase the rate of a reaction? So which of these will make our reaction go faster? And there's a couple of different ways you can think about what speeds up a reaction. There's some formulas we have, like the Arrhenius equation we did a lab on. There's some other things as well, called like the collision model, thinking about what makes things collide more frequently. But the main things that we're looking for, which of these factors should increase the rate of the reaction? Temperature increase. Think back to our kinetics lab. Super hot water dissolves things faster. It makes things react faster, right? So super hot solutions, increasing the temperature, does always increase the rate. And that should be kind of the easiest one to kind of understand, right? The hotter something is, the faster the water molecules or the air molecules move, and the faster they're able to interact with each other. So 1 is definitely the answer. And if you look at your answer choices, they also know that that's probably common sense, right? This one's only 1, 1 and 2, 1 and 3 are all of the above. So we know 1 for sure increases the rate of the reaction. All right. So the next one I want to talk about is number 3. Number 3 says reactant concentration increase. So that means you add more stuff. Okay, if you add more stuff, it kind of makes sense that stuff's going to collide into each other more often. The more stuff you have, the more likely reactions are to occur. The more likely particles are to collide into each other with the right amount of energy and the right orientation to be able to react and make products. So number 3 is also one that makes sense. The more stuff you have, the faster the reaction happens. So 1 and 3 are definitely both right. They're both ways to increase the rate of a reaction. And then number 2 is another common thing that gets asked, the activation energy. Activation energy being how much energy you need to start the reaction. Now, the higher the activation energy is, the more energy particles need when they collide for the reaction to be able to begin, right? Remember, when you're starting a reaction, you have to break all of those bonds of all your compounds that you're starting with. And that takes a certain amount of energy, and that energy is just that activation energy. Well, the higher that is, the slower the reaction happens, because lower percentages of the particles meet the criteria to react. They don't have that activation energy that they need. So this one works opposite. Lowering the activation energy increases the rate of the reaction, and vice versa. Increasing the activation energy is going to lower the rate of the reaction. So 1 and 3, answer choice C, is our right answer for this one. And I'm going to be maniacal and not circle it or anything. That we have to listen to my whole explanation to get the answer. Okay. And then we have this one. Let's go back to the document camera. All right. So this is the one with all these different vocab words that we need to know. And we have here a reaction And this one happens in 2 steps. So we have a multi-step reaction. So first thing, when you see a multi-step reaction, just know that each individual step is what we call an elementary reaction. Each individual step is simple, but the total reaction happens in multiple steps. Oops. So it gives us all sorts of information, which things are reacting, if it's slow or fast, and if it's exothermic or endothermic. And there's several things we're looking to answer here. So we're just going to go in order. Let me try to zoom in a touch more. Okay, we're going to start with the overall reaction. For that, we're just going to add the 2 reactions together. Anything that's on both sides, though, like this NO2, for example, I can cancel out. And the other thing I see I can cancel is this NO on both sides. So none of that needs to be included in the overall reaction because it's on both sides of the reaction. It didn't actually change. So my overall will be what I have left, O3 plus O. I'm going to drop the state of matter symbols. Makes O2 plus O2, but it's easier just to write that as 2O2. So I have O3, which is ozone, plus monatomic oxygen, gives you 2 regular oxygens. That's the first part. That's your overall reaction. Next thing we're going to do is write the rate law. Most common mistake is, okay, well, I have my overall reaction. Let's write the rate law from it. You cannot write the rate law from this overall reaction because it is not elementary. This happens in 2 steps. Elementary reactions happen in only a single step. So each individual step is elementary, but the overall is not. But it's really easy as long as you remember not to use the overall to write the rate law. So for the rate law, you just find the slow step. Your slow step's kind of like your bottleneck step. It's what's stopping the reaction from proceeding, and it's all that affects the rate. Go to your slow step, use the reactants here to write your rate law. So my rate law, right, rate equals K. That's how you always start a rate law. Your first reactant is O3, put it in brackets. It doesn't have a coefficient, so we just put a 1, and that means we don't have to put an exponent here. And your second is NO. And that is your answer for your rate law. The overall order, you have to look at the rate law, and you have to figure out, you have to add up your exponents. Both of these are 1s, so your overall order is second order. Catalysts are things you need for the reaction to occur. They work by lowering the activation of a reaction, allowing it to occur faster. But the idea is that they are not consumed during the reaction. So they're things you need to make the reaction happen, but they're just kind of like helpers. And they can be reused over and over because they don't get consumed. You'll learn about all sorts of catalysts in biology, and we talk about a little bit in chemistry too. So looking between these 2 steps, my molecule that is used as a reactant but doesn't get consumed is this NO. I add it to start the reaction. It's still left over at the end, so it's able to be reused again. So NO is my catalyst. Okay. That nitrous monoxide, not the word no. Okay. Intermediates are things that are made during the reaction just to be used again immediately after, or eventually after. In this example, my NO2 was made during the first step by adding an extra oxygen and then just immediately used again. You'll notice your intermediate does not appear in the overall rate law. Okay. Or the overall reaction. Neither do your catalyst. Okay. So your intermediate this time is NO2. Okay. This one says if you increase the concentration of the reactants in the overall reaction, I mean if I add more O3 and more O, what happens to the rate? Okay. So if I add more O3, the rate goes higher. O3 is in the rate law, so adding more O3 increases the rate of the reaction. Adding more oxygen, though, doesn't affect the rate of the reaction because that's in the fast step. Okay. So I'm not going to write anything there. And last, we have this reaction coordinate graph. Okay. So we have, usually you think about like energy of the reaction here on this axis. And you have like either reaction progress or time or something here on the bottom. I'm just going to write the word reaction. It's how a reaction proceeds. Okay, my overall reaction is exothermic, so that means it goes down in energy. I release extra energy into the environment. And for this, each step is exothermic, which makes it easy to draw. So my first step is going to be a drop in energy. That's step 1. and so is my second step, drop in energy, and then my overall will be a drop in energy as well. So I'm just kind of marking that on my graph. So I'm going to connect these two dots, but I need to add some activation energy. Exothermic, endothermic reactions, doesn't matter. They all have activation energy. Start with a little hump for the activation energy, and then eventually drop it down to meet your next line. So this little extra hump is your activation energy, but you see you overall lose energy because it's exothermic. Repeat the next thing for the next step, bring it down to the bottom, and that is your total reaction coordinate graph. So if you see this scary word, it doesn't mean anything really. It's just talking about drawing your exothermic or endothermic reaction over time. All right. Next, we have first and second order half-lives. The question here is asking about first order, but we're going to add the second order as well. Now it says, for the reaction below, what is the first order half-life? Gives us a reaction, that's good. Gives us K, gives us the rate constant, which doesn't mean anything explicitly, it's just kind of telling you how fast does the reaction occur. And all you really need to know, K, the bigger it is, the faster the reaction happens. The smaller K is, the slower it happens. Right? And then my initial concentration of N2O4 is 0.02 molar. And the question here is asking for the first order half-life. So the first order half-life, the important thing about it is it does not use concentration of N2O4. That's given to you in the problem, but you don't need it at all for a first order half-life. First order half-life does not depend on the concentration that you have. It's consistent regardless of how much you start with. But second order half-lives do. So we're going to kind of do the work for both. We're going to start the time of a half-life, and this is going to be a first order half-life. So you can kind of write that above or however you want to think about it. And all you have to do, we just have a number up here, which is a little bit weird, 0.693, or the natural log of 2. You could prove where this number comes from if you really wanted to, or you just write it down. It's on your formula sheet just like this. Either this or the natural log of 2. And then you just divide by K. That's all you have to do. So you plug in K to this expression, and then do 0.693 divide by that number. And that tells you the time of a half-life. So 0.693 divide by 5.5 times 10 to the minus 4th equals 0.693 divided by 0.00055, 1,260, or B. Okay, let's think about K real quick though. K right here is a really small number. If I increased K, say K was just 20, maybe something like that, how would that affect the half-life? Well, if K is a really big number, what that means is K, the reaction happens relatively quickly. If I plugged it into my equation, if I just plugged in 20 here, the time of a half-life would have been like a fraction of a second, right? So the half-life being really short would make sense because the reaction happens really fast. Half of your reactant is going to react incredibly quickly. So the higher K is, actually the shorter the half-life is. But that just kind of tells you how fast the reaction occurs. And the smaller K is means the slower the reaction happens, the bigger the half-life is. Now the second order half-life has a second formula. It's very similar though. The time of a half-life is 1 divided by K. So it's a very similar start, except you use just 1 instead of the natural log of 2. K. And then your initial concentration of N2O4 does get used in this one. So this is your formula you would use. I just plugged in my initial concentration. I'll plug in my K, 5.5 times 10 to the minus 4th for K, and solve. So this is 1 over 5.5 times 10 to the minus 4th times 0.02. Let's see what we get. 1 divided by 0.00055 divided by 0.02. I get like 91,000 seconds. Which, if you look, was one of the answer choices. So I was trying to trick you with this question. A is a very commonly answered incorrect question, because if you did the second order half-life instead, you would have chosen A. All right. This is good enough. All right. Next section is on thermodynamics. So that's all for kinetics. The topics we're going to go over for thermodynamics include all of these formulas, our calorimetry formulas about Q equals MCAT, Q equals MHF, Q equals MHV, how to use those. Determining the specific heat of a metal using a calorimeter, just like in our lab. Find the C of an unknown metal. And then a lot of looking at endothermic for exothermics, scenarios involving the words system and surroundings, which can make things very confusing. And then calculating delta H using the enthalpy of formation. Identifying reaction as endothermic or exothermic using delta H, that part's easy. Stoichiometry involving delta H, and then Hess's law to end it out with. All right. So, how much heat? Heat, when I see heat, I'm always thinking Q. There'll be a couple other formulas we talk about heat in this by the end of the year, but heat, Q always go together. It's a capital Q here. I think it got autocorrected. Lowercase q, capital Q, it doesn't really matter though. Just if you see a capital Q, you might be thinking of equilibrium with Q versus K and stuff like that. Technically, this should be a lowercase q. So how much heat is required to heat 28 kilograms of gold? So usually we don't work with kilograms because we're talking in chemistry usually about grams. So we might have to turn that into grams to do our work. And if you're not sure if you need to do that, you can look at your specific heat and notice when it gives you your specific heat, it has grams, not kilograms. So we're going to have to cancel out that gram eventually to solve our answer because our final answer is just going to be in joules. So we need to make sure to convert this to grams so that your grams cancels with your grams here. And we're heating it from 20 to 100 Celsius, and it says no phase change occurs during the heating process, which is nice. We don't have to worry about things melting and calculating how much energy that takes. So we're just taking solid gold. It's going to stay as solid gold. All right, looking for heat. I have a change in temperature, and the title of the slide all tell me I'm using Q equals MCAT. So I'm looking for Q, that's how much heat. My mass of 28 kilograms, just times that by 1,000. Or add 3 zeros to turn it into grams. Your specific heat is 0.129, that's lowercase c. Your change in temperature, you can subtract it or just tell it goes up by 80. 100 minus 20 gives you 80. That expression, which you simplify, will give you your answer. So 28000 times 0.129 times 80 gives me a really large number, which I'll round to 3 sig figs. 289,000. Technically, you're supposed to round it to 2 because you have 2, but I always round to 3 because who cares about sig figs? All right, next. How much heat needs to be added to ice at 0 degrees Celsius to turn it into steam at 100 degrees Celsius? So ice, steam, imply we're changing our state of matter. Ice has to turn into liquid, and then liquid eventually turns into steam. So if we're doing some state of matter changes, that's when you know you need these formulas. Q equals M times the heat of fusion. Q equals mass times the heat of vaporization. These numbers are provided to you, but you kind of need to know how to use them. So multiple things are happening in our problem here. Let's kind of think about the journey our H2O goes on. It starts as ice at 0 degrees Celsius. That is the freezing or melting point of water. So if I start to heat this up anymore, it can't go to be 1 degrees because it's ice. Ice is stuck 0 or below. So our first transition is this ice is going to that's not what ice does. Ice is going to melt into water. And it's not going to change its temperature yet. It's still going to stay at 0 degrees. Only once it's water can it continue on its journey heating up, which is what it'll do next. It'll heat up until you have water at 100 degrees Celsius. And it has to stop there, though, because that is the boiling point of water. Okay. So you have water at 100 degrees Celsius, and then that is just going to turn into steam, because at 100 is when you start to boil, and that steam is now at 100 degrees. And it could continue to heat up more, but that's what we're looking for is 100. So this one has 3 steps. Ice melting into water, no temperature change. Water heating into hot water at 100 Celsius. Hot water boiling into steam at 100 Celsius. This first step is going to be Q. Wrote capital as a habit. It should be lowercase. But I'm going to take my mass. Crap, I didn't give you a mass. Let's say I gave you a mass and it was 50 grams. Okay. Technically, you could find an expression which would be like some number times m, but don't worry about that. Okay. So Q equals my mass, and I'm going to use the heat of fusion, HF, which is, I believe, 334. Just going to plug in the mass. So my first formula I'm using, step 1, is my Q equals mHF. Okay? 50 for the mass of water, and this number here, 334, is the HF constant. That's how much heat I need to turn all my ice into water. Now I need to heat my water from 0 to 100. I'm going to use an MCAT formula. So my mass is 50. C, my specific heat, is 4.18 for liquid water. That you just get from a data table. And then your change in temperature, it goes up by 100. So you put 100 there. So the second formula is just a Q equals MCAT. You use that one when your temperature changes. So that's formula number 2. Plus formula number 3. I have my 50 grams of water now at 100 degrees Celsius. I need to turn that into steam. I'm going to use my third formula, Q equals mHV. My mass is still 50. Heat of vaporization is a constant. It's 2260. All right. And now we're going to add all of this together. 50 times 334, 16,700. 50 times 4.18 times 100, 2,900. 20,900. 50 times 2260, 113,000 joules. You'll notice this last step is the one that takes the most energy. That's because the heat of vaporization is much larger than the heat of fusion. And what that means scientifically is that it just takes a lot more energy to boil a gram of water than it does to melt it. Melting takes a lot less energy. Rearranging the molecules in a way so that they're a liquid instead of a solid takes less energy than rearranging them in a way to make them a gas. But all you have to do, add up those 3 numbers to get your total answer. And Q equals 151,000,366. All right, another calorimetry problem, my favorite type of problem. Determine specific heat of a metal using a calorimeter. So we have a full word problem here. A 50-gram piece of metal is super chilled to -125. Now, when we did a lab like this, we heated it. So the metal is the thing losing heat when you add it to the water. In this case, it's actually going to be the opposite. The metal is going to be super cold. So it'll gain heat from the water, and the water should actually cool off. So you can do it the other way as well. Just harder to super chill stuff. 50-gram piece of metal is super chilled. That's its initial temperature. The metal is placed into 100 grams of water at its initial temperature. The final temperature of the mixture is 19.7. So you see the water got cooler, and then the metal got way hotter, right? From -125 to 19.7. The specific heat of the metal is what we're looking for. So we should have all the information we need. Basically, we're using the idea that Q lost equals Q gained. But we'll make one of them negative. I'll make the lost one negative because the heat's going down. You're losing it. Okay. So the thing that loses heat this time, the thing that cools off, is actually the water. So technically, you should put the water on this side. The thing that gains heat is the metal. But if you flip them, it doesn't really matter. The signs, it all works out either way. But technically, you should put the water by the lost side here. So my Q equals MCAT is what I'm going to do in the next step. So I'll have a negative MCAT. This Q equals MCAT, and I made them both negative, equals regular MCAT. So over here, I'll use all my water information. negative 100. Specific heat of water is known at 4.18. The change in temperature here, it goes from 19.7 is the final temperature minus initial, which is 22. And since it cooled down, this should be a negative number, which it will be. On the right, I have my metal with a mass of 50 grams. Specific heat is unknown, that's what we're looking for. Its change in temperature, its final temperature is 19.7. Its initial temperature is negative 125. So I have two negative signs there, I gotta be careful. I'm subtracting negative 125, so I'm really just adding it. I'm gonna simplify both sides. Negative 100 times 4.18 times negative 2.3, if you subtract that, equals 50 times C times this number, 19.7 plus 125 is 144.7, I think. Okay. And then now I'm just going to solve for C. So I'm going to multiply everything on the left together, then divide by 50, then divide by that. And that'd be like the shortest way to do the math there. 100, negative 100 times 4.18 times negative 2.3, all of this, if you want to do it in multiple steps, you can, equals a positive 961.4, equals 50 times C times 144.7. Then I'm just going to divide by each of those numbers. Divide by 50, divide by 144.7. My specific heat is 0.133, which is a good area. Most metals have a specific heat that's like a decimal like this. So decimals is usually about what you're looking for. If you got something like 30, that means something probably went wrong. All right. So, next question. Identify each of the following processes as endothermic or exothermic. Okay, so there's a couple different ways to think about it depending on what you're thinking. So, and it gets confusing depending on how you have to think about it. My preferred way to think about something like this is if I have to add heat to make the change occur, then I have an endothermic reaction. And I prefer not to have to think about the word system or surroundings unless necessary. So if I have to add heat, or another way to think about that is if my system cools off the surroundings. Right? If I'm taking heat from my surroundings to warm something up, it's endothermic. So both those are ways to think of an endothermic reaction. Exothermic means you release extra heat, which warms things up. Okay? So that's kind of how I think about exothermic versus endothermic. So for each of these examples, that's kind of what I'm looking for. Mixing iron shavings and oxygen creates heat to warm up a solution. So by both definitions of this, mixing iron shavings of this creates heat. That means heat's a product. That tells me it's exothermic. And it warms up a solution. Also tells me it's exothermic. So the first one is definitely exo. Ice melts to make liquid water. Honestly, for me, reading like this is a little bit trickier than looking at an example like number one, because I have to really think, which way is it going? Ice melts to make liquid water. Well, how do you make that happen? How do you make ice melt? You have to add heat, right? You have to add heat to the ice to turn it into liquid water. Adding heat makes me think endo. The purpose of ice is to cool off your drink, right? So the drink can be your surroundings. Having the ice melt takes energy away from your beverage and cools it off. Okay? So ice works by removing heat from the surroundings, which is your drink glass. Mixing HCl and NaOH at room temperature warms the solution to 37 degrees Celsius. So if you're not sure what the room temperature is, it doesn't really matter. It kind of depends on where you're looking at. It's anywhere from like 15 to 25 degrees Celsius, kind of depending on the context. You wouldn't really need to know because it gives you the word that it warms the solution. Mixing these things warms up the solution, meaning it releases heat. So this is an exothermic reaction. And last, the decomposition of NH3 into nitrogen and hydrogen gas lowers the temperature of a chamber from 25 to 21. Okay, so I'm cooling off my surroundings, which means I am taking heat from them. So this is endothermic. So exo, endo, exo, endo. All right, then we get into some enthalpy math. And this first one is by far the most common math problem I'd expect you to solve. It says calculate the change in enthalpy of the reaction below. We have all these different molecules here. And over here we have a chart with the enthalpies of formation, so what the F means here, of each of these things. The enthalpy of formation is basically how much energy overall is either released, if it's negative, you'll see most of them are negative, or has to be added, like for oxygen here, to form this compound from its most basic parts. For H2O's example, that's taking some hydrogen and oxygen in their most simple forms, fusing them together releases 241.8 kilojoules per mole. For C6H12O6, that means taking 6 regular carbons, 6 diatomic hydrogens, H2s, and 3 O2s, adding all those together releases that much overall energy. Now, this allows you to do a shortcut if you look at a whole reaction. Just by comparing the enthalpies of formation, I don't have to break these molecules into their individual sort of bonds. So you could solve this problem looking at a bond table of how much energy a CH bond has, how much energy a CO bond has, how much energy 6 O2 bonds have, and draw their Lewis structures and add it all up that way, but that is miserable, and it would take you an hour to do it for this problem. So instead, what you can do is this shortcut. If you have the enthalpy of formation, just looking for enthalpy, you can take this sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. And we have all this data in our table here, with one exception we'll get to, and we could just add up all of our products numbers and then subtract them from all of our reactants number. And the difference is our answer, the change in enthalpy. So my change in enthalpy equals my products. Let's go ahead and put those on one side. So I'm putting them in a bracket just to help me keep my sign straight. My first product is 6 CO2s. So I'll take 6 times CO2's number, negative 393.5. And I'm going to add it, because we're taking a sum, to H2O liquids number. I have 6 H2O liquids, and its number is negative 285.5. Did not leave myself nearly enough room there. In fact, let's use the bottom of our paper. Delta H equals 6 negative 393.5 plus 6 negative 285.5. And that's all of my products added up together once I do the math. I'm going to subtract from that my reactants. So my first reactant is glucose. I have its number here. I only have one of those, so I'll just start with negative 1275. I'm going to add that to my other reactant, O2. O2 is not on this table because O2 is the most basic form of oxygen. Right? So its delta HF is 0. It takes 0 energy to form O2 from its most basic parts because it is its most basic part. In fact, here you just have a single O, but you'll never see oxygen as a single form, and the reason why, this is a positive number. To turn O2 into regular O, you have to add this much energy. So it's a really bad reaction. That's a really bad deal. That's why we would much rather have O2. It's its more simple form, and that's why this is the only one with a positive number, because you won't ever actually find this in real life because it always needs this much energy to turn it into O. So instead of adding anything here, just add it to 0. Okay, I'm going to simplify each of these terms. You can just type this whole thing into your calculator if you're confident in that, or you can break it down. The first term, 6 times negative 393.5 is a negative 2361 plus 6 times negative 285.5 is a negative 1713. So we're going to add those two negative numbers together. Then we are subtracting a negative 1275. So then I'm just going to add these two negatives together. Gets negative 4,074 minus a negative 1,275 is really just plus 1,275. And that simplifies to be negative 2790. I'll just write the full answer, because why not? What that means is, if I do this entire reaction, if I add the energy necessary to break all these bonds, and then I gain energy when these things reform, this is my surplus. I have a surplus of 2799 kilojoules per mole of reaction that gets released into the environment. Negative means exothermic, means it's being released. If this was a positive answer, that would be how much energy I had lost during the reaction. Or technically the energy gained a reaction, but the surroundings lost it. Very confusing. Here we have identifying reactions as endothermic or exothermic using delta H. Which of the following reactions is exothermic? So a couple of ways we can look for exothermic or endothermic. The first way, delta H is negative, it's exothermic. But this delta H is positive, so I know B is not the right answer. The second way you can look is heat. If heat is a product, that means you're making extra heat, and that's an exothermic reaction. So in part A, heat is a reactant, so you have to add extra heat to make the reaction happen. But in part C, heat is a product. So that means heat is being released, implies exothermic. And last, we have part D, we can just kind of look at a solid turning into a gas. So for a solid to turn into a gas, it needs to warm up. Meaning, if you have to warm something up, you have to add heat. So that's also endothermic. So the last way something is exothermic is if you cool off and like you go the opposite way. So if you're going from a gas and you're cooling it off to make it liquid, that's exothermic because you have to get rid of heat and the heat's going into the surroundings. Or if you go from a liquid to a solid, right, that's going down in temperature, right, that's exothermic. Or you can go all the way, gas to solid if you want. All those things remove heat from what you start with to what you end with. All right, I think this is our last one here, almost our penultimate thermodynamics question, is stoichiometry involving delta H. 55 grams of H2O reacts with excess carbon dioxide according to this reaction. So I have 55 grams of this and an infinite amount of CO2. Right. How much heat is taken from the surroundings? We use this language because it's endothermic. If it was exothermic, it would say how much heat is released to the surroundings. But this has to be taken because I have a positive number here. So how much heat is taken from the surroundings to make this happen? All right, so you may see this problem with numbers for each of these. You'd have to do limiting reactant. But the fact you have excess CO2 means all of this will be able to be consumed. So we're going to do a train track where we turn 55 grams of H2O, and we eventually try to turn it into heat. Grams of H2O is on top, grams of H2O on bottom to get rid of it. And like always, convert that to moles. Moles will let you do whatever you want. 1 mole of H2O weighs, we're just going to use the rounded number, about 18 grams of H2O. Okay. Moles of H2O is on top, put it on bottom to cancel. Now moles you can convert to any of these other quantities or enthalpy. So my moles of H2O, I'm just going to turn that into enthalpy. Or technically, I should use the unit of enthalpy, kilojoules. Okay. And now I'm going to go ahead and here you're going to put basically a mole conversion. H2O's number is a 2, so I'm going to put a 2 down there. H's number is positive 398, so I'm just going to put that up here. What this step means is you need 2 moles of H2O to release 398 kilojoules of H2O, or kilojoules of energy. Okay. So now we just solve. So this is kind of an extension of a mole to mole ratios. You can convert moles of one thing into energy if you know the enthalpy value. All right, so 55 times 398 divided by 18 divided by 2 gives me 608 kilojoules. That's my answer. So if I'm able to react all 55 grams of H2O, I must add 608 kilojoules to the reaction to make it happen. Maybe I'll do that with like a hot plate or like some fire or whatever I choose to do it with. Maybe another reaction as a catalyst. And then we get Hess's law. Definitely the messiest of all the different things. The idea is if you want to know about this reaction, which we do, we want to know how much energy this reaction takes, you can piece it together using other reactions if you already know their delta H's, right? If you need to manipulate any of the reactions, if you flip it, you just change the sign, positive to negative, vice versa. So you can flip a reaction around, it just changes the sign of your delta H. And then if you need to multiply by a factor, maybe you need to multiply everything by 2, you just multiply the H by 2. So it's really convenient with thermodynamic quantities. As we know with equilibrium, it's not as convenient as this. You have to do other things, but enthalpy values are simple. So I need to make this reaction, and there's a lot going on here. It's very overwhelming. So what I like to do is just kind of spot the individual components down in these reactions. The first thing, I'll just go by 2 N2s, and the only place I see N2 is down here. So I need to make these match, and since I only have 1 nitrogen here and I need 2, I'm definitely going to have to double this whole reaction. Right? That's how I'll get that. So we'll come to doing the actual work in a second. Let's look at the other terms. 5 oxygens. So I have some oxygens here. I have 3, but I'm going to times it by 2. So I actually have 6 oxygens already in the right spot, which is too many. But I might be able to reduce them if I look at this reaction. I have half an oxygen here. So currently I have 6.5 oxygens. But since I need my nitrogen on the left, I'm going to have to reduce it by flipping this to the other side. If I flip this one to the right, and it's a product, and then I double it, so it's just 1 oxygen, you would end up with 6 oxygens on the left, 1 oxygen on the right, and then it would equal 5. So for this top reaction, I'm going to have to double everything and flip it to make the oxygens work out. And we'll kind of work on the canceling and everything as we rewrite it. Okay, and then my last thing is 2 N2O5s. I have an N2O5 over here, but again, it's on the wrong side. So I'm going to flip this reaction as well. And to get 2 of them, I have to times it by 2. All right, there's some other terms in here, but hopefully they all cancel out. Spoiler, they always cancel out. So that means if you feel really confident about that, you can just go ahead and multiply all of these. The top one's going to be multiplied by -2 because you flipped. Let me write that a better way. So multiply all of this by -2. Multiply this one by -2 because it flipped and doubled. And this last one, you're just going to double. And you can add all. Then you can add all that up and get the answer. But just to be thorough, I'm going to go ahead and show what it looks like here. So when we do all these modifications, let me just pull them up. All right. The first one here, oops. Struggling. Give me a moment. One more slide. This goes up. Okay. So flipping and doubling the top 2 reactions. So the first one is going to show up as 2 H2O turns into 2 H2 plus regular 1 O2. The second reaction, I'm going to also double and flip, which gives me 4 HNO3 turns into 2 N2O5 and 2 H2Os. My last one, I'm just going to double, so I'll just double all the numbers. Okay, so those are all my values. To make sure everything cancels, this oxygen is going to reduce this down to 5. Okay. I have 2 hydrogens on the right, 2 hydrogens on the left. Those cancel. 4 HNO3s, 4 HNO3s. 2 H2Os, 2 H2Os. So cancel whatever's on the opposite sides, and I'm left with 2N2, 5O2 produces 2N2O5, which is the reaction I'm looking for. Now your enthalpies, I'll just kind of recopy them all here. Those are what your base enthalpies were. The top one, we're going to times that by -2. The second one, we're going to times that by -2. The third one, we'll just times by 2. We'll get our 3 values, and then just add them all up together. Your top value is a positive 571.6. Your second one also comes out as positive 153.2. Your last one, since you're just timesing by 2, is negative 696.4. When you add all 3 of those together, I get a positive 28.4 as my answer. All right. Super fun. Our last thing here are some equilibrium topics. So this will take care of it. I'll just be really tiny. All right. Definition of equilibrium and real-world examples of it. So what equilibrium is by definition. Writing equilibrium expressions and reaction quotients. Equilibrium expression means K. Reaction quotient means Q. Comparing K and Q to determine which way the reaction will go. Calculating K and Q given products and reactant concentration. Manipulating expressions. Le Chatelier's principle. And then solving ICE tables. So let's go ahead and get started. All right. Conceptual problem we'll just kind of do here. Which of the following situations best describes a scenario that's at equilibrium? Okay, so at equilibrium, what I'm looking for is what I'm adding to the reaction is the exact same as what I'm taking. And the reaction's constantly going. So I'm constantly adding and removing stuff at the same exact rate. So as I read through these, the one that strikes me the best, all of these are similar in some ways, but the answer that strikes me is answer B. It says, I fill my bathtub with water at the same rate that it drains out. As a result, the water level doesn't change. What that translates to with equilibrium is the forward reaction is occurring at the same rate as the reverse reaction, therefore the concentration of my stuff doesn't change. Now, each of these other ones have some merit. B is the correct answer. But like A says, I cut my lawn each Saturday to control the rate at which it grows. The system's at equilibrium because the lawnmower resets the system every week. And that's similar, but the idea is it's not constantly happening. Equilibrium, you always have your products and reactants growing. So in A, my lawn is constantly growing. That's equilibrium, but it's not being reset constantly. So an equilibrium for that would be like you are constantly mowing off 0.001 inches of your grass at all times or something. And then it's growing. And then the rate happens to be the same. Your grass will never change. C, I bake 21 cupcakes each week. Cindy eats 3 each day. My system's in equilibrium because we have the perfect amount. That's true, but it's not in equilibrium because I'm not constantly making cupcakes. I'm not constantly eating cupcakes, right? The levels the concentration of my cupcakes is going up and down, or I guess going down and then just rapidly up. They both need to be occurring all the time. And same thing with D, right? I balance the scale with exactly 40 pounds on either side. The scale is perfectly still and not moving. That's similar, but again, it's not moving. If on one side I was adding weight and the other side was adding the exact same amount of weight and it happened to cancel out, that's more realistic what equilibrium would be. So B is definitely the best answer here. All right, so next we have writing equilibrium expressions and reaction quotients. For the reaction represented above, the value of the equilibrium constant, Kp, is this. So it's just telling you the K at this temperature. You'll never need this. It's just trying to give you extra information. If you change the temperature, though, this changes. So that's why it's telling you this, because usually later in the question, it'd be like, assuming the temperature is still the same, what is the Kp? But this will actually change the equilibrium, because if you have an exothermic or endothermic reaction, changing the temperature will affect which way the reaction equilibrium shifts, according to Le Chatelier's principle. Write the expression for Kp. So Kp equals your, this is Kp usually implies you're using pressure, is what the P stands for. So I'm going to write this one with pressure, which just means instead of using like the brackets with my products and reactants, that's used for regular K or Kc. I'm just going to use the opposite term, which is their partial pressures. Right? Use pressure sometimes when all you have is gases. So my products, my first pressure is NH3, and there's two of them, so I'm going to square that term. And then I'm going to divide by, I'm just going to draw my divide by like this, just so I can have a little bit more room. And I divide by my reactants. So I have the pressure of nitrogen times the pressure of hydrogen cubed, because there's three of them. Now, if you wrote it with brackets, it really means the same thing. But just to be safe, I wrote it this way. This says write the reaction quotient of this reaction. You write it the exact same way as a K, but reaction quotient just means you're talking about the Q. Your reaction not necessarily at equilibrium. Q equals products over reactants. So I'll go ahead and put my, is it balanced? It's balanced. Put my CO2. And then I'm not going to put my water because it's a liquid. Solids and liquids do not get included in your equilibrium or your Q. So that's all that's going on top is CO2. CH4 is my first term at the bottom. And then O2, also a gas, going to include that. And since there's two of them, square. That's your Q. Okay. So this is kind of building off the last question. So we'll leave this last one still. So I'll kind of leave this here. We have technology. We can do this. Fold paper and everything. So I don't need the title. Fold the paper one more time. Perfect. All right, we have our KP. It says assume the initial partial pressures of the gases are as follows. Okay, when I see this, I see initial. That does not mean equilibrium, so I'm not going to use K. Instead, I'm going to use Q. Initial partial pressures or not at equilibrium means you use Q instead of K. Right. So I have my pressures of my gases written out, and I'm just going to use Q equals the pressure of NH3 squared divided by the pressure of N2 times the pressure of H2 cubed. Then I'm just going to plug in my initial values. NH3 is 0.224 squared. N2 is 0.411. H2, 0.903. Don't forget to cube it. That's our expression for Q. It's the same as K. I just use the letter Q to represent to you that it's not at equilibrium. Plug all this in my calculator. Divide by the bottom. And I believe I am doing it on my phone, so don't fully trust me. But I got 0.166 as my answer. That's Q. All right, that means currently that is my ratio of products to reactants. And what I can do is compare that to K to see which way my reaction needs to go to eventually get to my to equilibrium. Now, K was given to me up here. K is this number at 700K. See, I'm still at 700K. So my K is 3.1 times 10 to the minus 4. My Q is 0.166. This is K. This is Q. Which one is bigger? This one's bigger. The negative 4 means you move the decimal 4 times to the left, and it'll be a really small fraction. This one's bigger. Q is greater than K. My reaction is going to proceed to the left. In your justification, you'll say reaction proceeds left because K is less than Q. Now, the reasoning for this is Q's number is too big, which means you have too much stuff on the top, too many products, and not enough reactants. So the reaction has to shift left so that this number gets smaller, this number gets bigger. It'll keep doing it until your difference is 3.1 times 10 to the minus 4. But writing them in alphabetical order, you can kind of use this arrow trick we talked about to talk about which way it'll proceed. Next, we have manipulating equilibrium expressions. The value of Kp for the reaction below is 8.3 times 10 to the minus third. Calculate the Kp at 700 K for this reaction below. So, still at 700 K, which just means don't worry about it, it's all the same. I'm taking this reaction and just timesing it by 3. So if this was an enthalpy problem, you would just times this by 3 and you'd be done. But with equilibrium, you do things differently. So with equilibrium, if you flip the reaction, right? So if you flip the products and reactants, turn it around backwards, then you're actually going to do 1 over K. You have to take the inverse. And if you multiply by a factor, you don't actually just multiply your K by a factor. You have to take your K to that power. So if you multiply a reaction by 3, take K, raise it to that power. Right, so it's a little bit different. And then if you have multiple reactions, you have to multiply them together. All right, we proved this a little bit in the notes, but just kind of trust it that it's weird for K. All right, so this reaction, I have to flip and times by 3. So both of these things will be done to it. So I'm going to flip my K and I'm going to cube it. The order you choose to do this doesn't really matter. So my K, I'm just going to plug in my 8.3 times 10 to the minus 3 cubed. You can cube it and then flip it, or flip it and then cube it. You'll get the same answer either way. Let's see what I get. 0.0083 is that number. And then I'm going to cube it. I'm going to turn my phone sideways. And then I'm going to flip it. I'm going to take the reciprocal. What else? I get a really big number. I get 1.75 times 10 to the power of 6 is my K. Makes sense, it should be a big number, right? Because I have a decimal here, which I'm cubing, which makes it an even longer decimal. And then you're flipping it, which will turn the decimal into a big number. So that makes sense. All right. All right, we have, I believe it's the last page coming up. Let me see. Pause while I look for my paper. I'm silly. This is the right paper. I was just looking at my PowerPoint and just haven't moved the slides forward. So we have 2 things left. We have Le Chatelier's principle. It says in the following reaction, will the concentration of H, so that's what we're looking at, how much of this we have, increase or decrease when equilibrium is reestablished after these stresses are applied. So we're going to stress the system by adding or removing something and see what our concentration of H2 will be after. First, I add some ammonia. I add some of that. Well, the reaction doesn't like that. It's going to try to mitigate your change. It's going to react against it, which means it's going to shift to the left to decrease the amount of NH3 you added, which, if you shift to the left, means you make more of this. So concentration of H goes up. If you remove some nitrogen gas, the reaction is going to try to mitigate that change. So to mitigate removing some of this, it's going to try to make more. The reaction goes to the left again. Concentration of H will increase. This should be H2, but you know what I mean. So removing another reactant or increasing the amount of product will both shift the reaction towards the H2. If pressure is increased, the reaction is going to try to mitigate that as well. To look at pressure or volume, because they're just inverses, you see how many moles of gas you have on either side. So I have 1 nitrogen and 3 hydrogens. So I have a total of 4 moles of gas over here. And I only have 2 moles of gas over here. If I increase the pressure, the reaction is going to try to counteract that change by reducing the pressure. To reduce the pressure, the reaction shifts to the right because it makes less gas that way. You take 4 moles of gas and turn them into only 2. So if you shift the reaction to the right, it will decrease the pressure, which is the opposite of my change I tried to instate. If I shift to the right, though, that means my concentration of H2 goes down. So even without changing directly any of these quantities, I can affect the amount of H2, or the overall equilibrium of the reaction, just by changing the pressure of the vessel. Similar thing with temperature being increased. Okay, I have plus 22 kilojoules. So this is one of my products, meaning this is an exothermic reaction. So if I increase the temperature, that means I'm basically just adding more of this product, right? The reaction is going to shift to the left to try to counteract me. Shifting to the F means you make more H2. So if you have a product or reactant, you just look where it is in the reaction and shift opposite to make that change not occur. Pressure, look at the moles of just gas on either side. Temperature, look for where the temperature is. Exothermic means it's a product. Treat it as a normal product. If you increase it, go to the left or go the opposite way to reduce it. Or if it's a reactant, if you increased it, you would have to go to the right to reduce it. All right, solving ice tables. This is our last question here. Determine the equilibrium concentration of Br and Br2 given the initial concentration of Br2 is 0.18. There's no Br in the original reaction vessel to begin. It gets really wordy, which is part of the reason we like to just start by writing an ice table. You talk about your initial, what change occurs, and your equilibrium values. Initially, Br2 is 0.18. Throw that in your ice table. And initially, there's no Br. So that's what the problem is telling you. It's telling you how much of each thing you start with. Now, we have to predict which way the reaction will go. And because there's no Br to begin with, you have to go to the right. So this reaction is definitely going to start and reach equilibrium by going to the right. Meaning I'm going to lose a little bit of my reactant and gain twice as much product because I have a 2 here. So I lose one of these and I make 2 of these. Meaning my equilibrium amount of bromine is 0.18 minus X. And my equilibrium amount of monatomic bromine, Br, is just 2 times X. Well, I just need to solve for X and I have my answers. So I need to go and write my K. K is products over reactants. So I have Br times 2, because there's a 2 in front, over Br2. I plug in my values, even though they have X's, I could still solve for the X's, into my expression. And I already know K, I'm going to plug that in as well. This gives me 2.5 times 10 to the minus 6 equals Br's concentration is 2x squared over Br2's concentration is 0.18 minus X. Now, this is perfectly able to be solved for. You can solve for X by moving everything to one side and setting it equal to 0 and doing the quadratic formula. Boring. What you can do instead to save yourself a lot of time is just get rid of this term, minus X. We can make this approximation whenever K is a really small number, which it always will be, okay, for our examples at least. With K is a small number, K is products over reactants. And if K is a small number, that means you have very few products, it's a small number, and many reactants. And what that just relates to is this reaction doesn't go very far to the right. Right? X is going to be, your change is going to be very small because at the end, you're going to have pretty much all reactant and only just a smidge of products. So this minus X change isn't actually that significant. This X is going to end up being a really small decimal. So you're going to have 0.18 minus something that's like 0.0001. And that's basically just 0.18. When you subtract a very small number, it doesn't really change the number very much. So we can get rid of the minus X term. We can't get rid of this X term though, because multiplying by a small number does affect your value a lot. Multiplying by 0.0001 changes a lot. But this is going to make it a lot easier to solve for X. So I have 2.5 times 10 to the minus 6 equals 2x squared. Make sure to square both terms to get 4x squared. over 0.18. Multiply 0.18 up here to get it by itself. And you end with 4x squared equals this product of 0.18 times 1, 2, 3, 4, 5 zeros, like that. You get 4.5 times 10 to the 1, 2, 3, 4, 5, 6, 7th, negative 7th power. Divide each side by 4. I end up with a 1.1 times 10 to the minus 7th power equals x squared. Take the square root. 0.000335 equals x. Like we said, x is a really tiny number. So 18 minus this is basically just 18. You would get a more exact answer if you didn't do this approximation, but you would spend all day doing it. So, all right, that's not our final answer. This is how much change occurs. That's our value for x. We can just solve for these two real quick, and that'll be our answer. 0.18 minus x, we're just going to round that to 0.18. That's how much bromine we're going to have left over. And 2 times x, we're going to multiply this by 2, and we should get 0.000335 times 2 be 0.000670, I believe. All right. And that's it. So hopefully you found that helpful. I think just going through all these practice problems will really, really help you on the test. If you know how to do all these problems, I have no concerns with you being able to pass and get a really good grade on the test this week. All right. Good luck studying. See you soon.